Welcome all, my name is Stefan Klootwijk and I'm a PhD student at the University of Twente under the supervision of Bodo Manthey. The work I'll be presenting in this video is joint work with him, but before I come to those results with the title Probabilistic Analysis of Optimization Problems on Sparse Random Shortest Path Metrics, I would like to start with an overview of the general idea of our research, of which these results are just a part. Large-scale optimizations problems, such as the traveling salesman problem, show up in many applications all around us. Unfortunately, as you probably all know, for most of these problems we cannot find the optimal solution within a reasonable amount of time. Therefore, in practice, these problems are often being tackled by ad hoc heuristics or approximation algorithms that do not necessarily provide optimal solutions and which are often quite simple. On the positive side, many of these heuristics perform remarkably well in practice, even though the theoretical worst-case results about those heuristics are way more pessimistic. So there is in many cases a big gap between the theoretical performance and the actual performance of such heuristics. To give some examples, we have here the greedy algorithm for minimum weight perfect matching, which has a worst case approximation ratio of approximately n to the power 0.58 on metric instances, whereas in practice one obtains almost always a constant approximation ratio. Similarly, the nearest neighbor heuristic and the two-opt local search heuristic for the traveling salesman problem have a worst case approximation ratio of order log n or square root of n on metric instances, whereas in practice the solutions returned by these heuristics are way better than these relative pessimistic bounds. I'm talking here about results on metric instances, since in practical situations the instances of many optimization problems involve either implicitly or explicitly a metric space. You can think here about physical distances between locations or travel times, but there are also other things possible, like transportation costs. This, let's say, sort of standard involvement of metric spaces is the reason that we compare with the worst case performance on metric instances. But even though we use this assumption of having a metric, there still remains a quite big unexplained gap between theory and practice. In order to explain this difference, the method of probabilistic analysis has been widely used over the last decades, and more recently also other so-called beyond worst case analysis methods become more popular. When doing probabilistic analysis, the performance of the heuristics is analyzed with respect to a random instance, and often expected approximation ratios are obtained in this way that close somewhat the gap between theory and practice. One of the main challenges in probabilistic analysis is to come up with a good model for generating those random instances, over which we in the end then can take the expectation here. On the one hand, such a model should be sufficiently simple in order to keep the analysis possible, but on the other hand, we also would like the model to somehow reflect realistic real-world instances. In the early days of probabilistic analysis, random instances were either generated by using independent edge lengths for each pair of vertices, or by placing some random points in a square and using the Euclidean distance between them. Both models perform rather well on the side of making the analysis possible, but not so well on the side of generating realistic instances. For the independent edge lengths, I hope this is immediately clear, since there is no guarantee at all of ending up with a metric instance. And even though Euclidean space does guarantee that the instances are metric, in practice, if you think for a moment about it, instances are almost never actually Euclidean. So what we want to do with our research is to broaden the range of available metric spaces, and we look at different models for random metric spaces, study their properties, and try to use them to analyze the performance of heuristics on them, which on the long term hopefully improves our understanding of these heuristics and can help people choose the right heuristic for a given problem, or maybe even facilitate the design of better heuristics. Having said all that, let's go to the random model that we've been working on, called random shortest path metrics. In short, you could see the random shortest path metrics as a way to transform the space with independent edge lengths into a metric space. What we do is that we start with an arbitrary simple graph G on n vertices, and we will refer to this graph as the one that is being used to generate the metric spaces. Next, we add random edge weight W to all edges of G, independently and identically distributed, and then for every pair of vertices U and V, the distance between them is given by the total weight of the shortest UV path in G with respect to the weights W. And it's important to note here that this also includes pairs U and V for which there is no edge in the original graph G. This way it should be easy to see that we end up with a metric, since these three properties here are satisfied. Moreover, the metric is complete in the sense that we can go directly from any vertex to any other vertex, even if this is not possible in the original graph G. To give an idea of how this works, I've prepared a small example. Here we have a graph G on 5 vertices, and we have drawn some edge weights, which you can see here. And if we want to know the distance between A and B, we can see that the shortest path between A and B is this red path via C, E, and D. And so the distance between A and B becomes the length of this path, which is 20. The shortest path between A and C is the direct edge, so the distance between A and C is 3. Between A and D, this is the shortest path, so we get a distance of 13. And between A and E, this is the shortest path, so we get a distance of 11. And in a similar way we can find all distances. One of the concessions that we made in our model due to keeping the model analyzable is to use the exponential distribution to generate the edge weight. The main advantage of using the exponential distribution lies in the two properties that we've listed here, the memorylessness property and the minimum property. The model of random shortest path metrics is not new. It was introduced in the 60s under the name first passage percolation as a model for fluid flow through a porous medium. And in the years thereafter, the model itself has been widely studied, but until recently it has not been used for probabilistic analysis. So, although they do not use the term first passage percolation or random shortest path metrics explicitly, the idea of using this model for a probabilistic analysis has already been proposed by Carp and Steele in '85. It took some time before the first actual results of a probabilistic analysis on this model were found. This was a couple of years ago in a paper by Brinkman, Engels, Manthey, and Rao, and they used a complete graph on n vertices to generate the random shortest path metrics, and showed that in this model several simple heuristics achieve a constant expected approximation ratio. And I've listed here the ones that are relevant to our recent results. In the paper there are some additional results. Basically we have here 3 greedy or greedy-like heuristics for which there is a constant expected approximation ratio. We have the greedy heuristic for minimum distance perfect matching, the nearest neighbor heuristic for the traveling salesman problem, and the insertion heuristics for the traveling salesman problems, where the result holds for any insertion rule R. Given our own results that will follow soon, it is also worth to mention that in this paper it is also mentioned that there is an easy way to show that the 2-opt local search heuristic for the traveling salesman problem achieves an expected approximation ratio of order log n, which might or might not be improved upon. Although this model is still very interesting, in practice we see that networks are almost never complete. So in order to make the model more realistic, we went into search for results on random shortest path metrics generated from non-complete graphs. And this led 2 years ago, together with a master student, to a generalization of the results of the previous slide to the model where we use Adder's random graphs instead to generate the random shortest path metrics. Again, I've listed here only the results relevant to this talk, and we can see that this model is already a bit more realistic since we have a non-complete graph to start with, but the results here only hold for Adder's random graphs where the probability of an edge being present is sufficiently large, and we roughly need the same bound that is needed for an Adder's random graph to be connected with high probability. So the graphs that we use to generate the random shortest path metrics are still dense here, whereas networks in practice are mostly sparse. So we set aim to research random shortest path metrics generated from sparse graphs, and we started this research by using square grid graphs, since such graphs are the most studied within first passage percolations. And in the end of last year we obtained the first results on this sparse model, which are the main results of this talk. And Again, we have a constant expected approximation ratio for the three greedy-like heuristics from the previous results, only now for the model where the random shot sparse matrix is generated from square grid graphs. But we also were able to obtain a constant expected approximation ratio for the 2-opt local search heuristic for the traveling salesman problem, for which the proof was easily generalized to hold for random shot sparse matrix generated from arbitrary sparse graphs. And after submitting the paper that I'm presenting here, the results for the three greedy-like heuristics also have been generalized a bit, and they hold now for a certain wide class of sparse graphs, but not for all arbitrary sparse graphs. In the remainder of these presentations, I will show you the ID for the probabilistic analysis of the 2-opt result, and I will say some more or less also about how we went to the greedy matching result. So the ID for the 2-opt result mostly relies on this crucial observation that you see here. So we noticed that if you look at the disjoint union of the shortest paths used by any 2-optimal solution, then this disjoint union can only contain each edge of the original graph G at most once per direction, so twice in total. And to see that that is the case, suppose that we have an edge of the original graph G that is used twice in the same direction, like here in this example. So we have a TSV tool where we go directly from the left top vertex to the right bottom vertex, and later on in the tool we go from the right top to the left bottom. And both shortest paths include this edge between these blue vertices and the original graph G. And if we now consider the two exchanges where we take these two connections out and go instead from left top directly to right top, and later on from right bottom to left bottom, then due to the triangle inequality that we have, the total distance of these new connections is at most the total length of the curved edges, and that is strictly less than the total length of the original connection, since we do not have the edge between the blue vertices twice. Therefore, the solution here on the left hand side can never be 2-optimal, and the result of the observation follows. The remaining bit of the proof uses this observation to show that the total length of any 2-optimal solution is bounded by twice the sum of all edge weights, and since there are order of n edges in G, because G is a sparse graph, it follows that the expectation of the worst possible 2-optimal solution is bounded by big O of n. On the other hand, we also can show that any TSP solution uses at least n-1 different edge weights of the original graph G, from which we can derive that the expectation of the optimal solution is bounded by big omega of n, and the final result in the end follows with some small additional effort. Now let's move on to the greedy results. Broadly speaking, our proof follows the ideas of the original paper by Brinkman and co-authors, although some parts needed to be strengthened to be able to generalize to the use of sparse graphs, specifically square grid graphs. The starting point for these proofs is the distribution of the distance from a given point to the cave closest vertex from it. In the model generated from complete graphs, the distribution of these distances is exactly known, as stated here in this theorem. I don't have the time to bother you with the details here, but the important thing to note is that this I times n minus I shows up because it is the fact that in a complete graph, the number of edges between a subset of I vertices and the remaining n minus I vertices is exactly I times n minus I. So we can generalize this result by Davis and Preditis if we have a bound on the number of edges in the cut defined by a subset U. And the generalization is here shown as follows. And luckily, when we look at square grid graphs, such a bound on the number of edges in a cut was already known, so we can use that to continue with our generalization of the original proof. And as a small remark here, this is the point where we can further generalize our result from random shots path metrics generated from square grid graphs to random shots path metrics generated from a wide class of sparse graphs. And basically we require that the cut sizes of G grow sufficiently fast as long as the size of U is not too large. In this talk, however, I will stick with the results for square grid graphs as we also did in our paper. So if we plug this bound on the cut sizes into the result of the previous slide, we get this bound for the distribution of the distances from an arbitrary fixed vertex to its cave closest neighbor. And the next step is to derive some results that form kind of a toolbox for the final proofs. The clustering result is obtained by following the same IDs as in the original proof by Brinkman and co-authors and adapting them to our new bound on the distribution of the distances. And additionally, we also needed to make precise the idea that in our model very long edges only exists with a ridiculously low probability. And with these tools in our toolbox, we're ready to go to the main proofs, where we will be focusing on the greedy matching algorithm that iteratively adds a connection between the two closest unmatched vertices, as you can see happening here. We've shown that this greedy heuristic outputs the matching with expected costs at most order n, and as a consequence of that we could show that the expected approximation ratio is constant for this heuristic on random shots path metrics generated from grid graphs. The proof required an improvement to the proof ID of Brinkman and co-authors. We used the same partition ID as they did and as visualized here, where we put the connections that are being added by the greedy heuristic in bins according to their length. But instead of being interested in the number of edges in a bin, which we call xi, we are interested in the total values yi, where yi is the total from bin I onwards until infinity. The expected value of the greedy heuristic can namely be written as a sum over all these y's. And note that y1 is the number of edges that are in total being added by the greedy matching, which is n/2. For larger values of y, we use the clustering result from a toolbox, which we can use to see that partitioning of all the vertices and clusters of diameter at most 4 times I minus 1 needs this number of clusters. So when greedy moves to bin I and starts adding edges of distance more than 4 times I minus 1, we know that at this point in our clustering there can be at most 1 unmatched vertex per cluster, since otherwise there would be a possible unmatched connection that is shorter than 4 times I minus 1. So when greedy starts putting edges in bin I, we have at most this number of unmatched vertices remaining. So in the remaining bins, the number of edges that can be placed in there is bounded by the same number. For large I, we use the tail bound result from our toolbox to bound the expectation of yi, which is this result, and in the end we sum over all I to get our final desired result that the expected value of the greedy heuristic is at most big O of n. And the constant approximation ratio now follows in a way that is similar to the 2-opt result earlier. Finally, I would like to end with some open problems related to this. So first of all, we wonder whether the greedy results can be generalized to random shots path metrics generated from arbitrary sparse graphs, like we did earlier for the local search 2-opt result. We did already do this for some wide class of sparse graphs as shown earlier in this presentation, but it seems to be the case that our method cannot be used to further generalize to arbitrary sparse graphs. Secondly, one might wonder what happens if we define the problems only on a subset of the vertices of our random metric space. It seems that such a model would be even more realistic, but again we don't know whether it will be analyzable or not. And finally, in our analysis of the local search 2 opt result, we had to decouple the actual heuristic from the initialization in order to make the analysis possible. So it would be really interesting to see whether it's possible to analyze a hybrid heuristic where we also take the initialization into account. Thank you for your attention.